So yeah, good evening everyone. This is I am Diljit Datta. I am a research scholar in Indian Institute of Science. So today we'll be starting the session 8 of that is geological problems in week that have been done in week 8 of the course hydraulic engineering, which is being taken by Mohammed Salafzin. And in this session we will be looking into some problems related to pipe flow and pipe related to pipe flow and friction losses in pipes and also power transmission in pipes like that. So yeah, let us get started. uh, First of all, we will be looking into uh, yeah. So yeah, first of all we will be looking into the measurement devices in pipes, like how do we measure flow in pipes. So there are three main devices for flow measurement is in pipes. One is pitot tube. Pitot tube we have discussed in our previous lectures. Second is a venturimeter, and third is a orifice meter. And so we'll just go to the principle of the instrument called venturimeter. In venturimeter, what happens? So initially, this is the pipe. If you take this as a pipe cross section, it may be inclined also. It doesn't. I'm just giving horizontal for schematic purposes. So this is the pipe. The pipe is constricted at one section. This is called converging section, and then it is diverged to get then there is a diverging section. Finally, this is again the same diameter as the D1. This is also D1. So there is a converging section, there is a diverging section, and so and what we do is we fit a differential manometer or a U-tube manometer to the 2 points. One is the point where there is a minimum cross-sectional area, and the point just before we do the conversion, just before the start of the converging section. So fitting the 2 points to a U-tube or differential manometer, and the other this is mercury level will be here, and since there is a width constriction, so there will be a difference in the pressure head between the two sections. This difference in pressure head is given by H. And one more thing, when we this is the schematic diagram of a venturimeter. One more thing is the diverging section is always longer than the converging section. So what is the reason for this? The reason is that we want to reduce the losses due to formation of eddies or the nonlinear losses. When the diverging section is longer, so these eddies that are formed due to flow diverging from this small cross section will be less. But if we suddenly expand it in a short distance, then there will be a lot of nonlinear losses as in this area, and this might also cause some error in the measurements. Okay, so how do we get the flow velocity? So first is we will apply the Bernoulli equation between the two sections, that is section 1 and section 2. Section 1 is just before we start the converging section. Section 2 is the part of the pipe where there is a minimum cross-sectional area. So this is the Bernoulli equation, and this is the P1 by rho g plus V1 square by 2g equal to P2 by rho g plus V2 square by 2g plus HF. HF is the head loss due to friction. So the difference in now, what is H? H is the pressure difference between section 1 and section 2, and so P1 by W minus P2 by W will be the head, and P1 will be greater than P2 because this is quite obvious, as the velocity at section 2 will be higher than velocity at section 1, so P1 and P2 will be less than P1. So now we replace this term in the initial equation, so we will get H minus HF, and this is equal to H dash equal to V1 square by 2g minus V2 square by 2g. We replace V1 by Q by 2 Q square by area. So if we take the area at section 1 as A1 and the area at section 2 as A2, then we will get H dash equal to Q square by 2g 1 by A2 square minus 1 by A1 square. And if we rearrange the term, we will get this is the equation of flow. Q is equal to a1 a2 under root 2 z h this by a under root a1 square into a1 square minus a2 square. Now this is the terms a1 a2 into 2g by a1 square minus a2 square is called the constant of Venturi meter. Okay. Now what happens? This is the theoretically the discharge like the flow that we get from that we should get when we do the measurements. But when we are doing measurements, we won't get this discharge. So there will be some losses. So some losses due to eddies formation. Even if we are doing this converging and diverging, giving a large length in the diverging section, then also there will be some losses, and also there will be some losses due to width constriction also. So considering these losses, there will be some losses, and the actual discharge that we get by measuring by measurement from the manometer will be slightly less than the theoretical discharge. So the actual discharge is related to the theoretical discharge by Q is equal to K into C root H. What is K? K is called the coefficient of discharge, and this value and the coefficient of discharge for a Venturi meter ranges from 0.95 to 0.99. Similarly, there is also one instrument called the orifice meter. So what happens in orifice meter? So here there will be a sudden width constriction, there will be a sudden width constriction. We will be connecting this area, this point, to a U-tube manometer. Fill this with mercury. So the head difference between the two sections will be H. Section 1, section 1 and section 2, and the head difference between the two sections is given by the difference in the mercury levels in the U-tube manometer. Now if we use the same equation, like same Bernoulli equation that we used in Venturi meter, we will also get the similar equation, that is discharge equal to C root H dash, where C is equal to A2 but the thing is that when you get the actual discharge, the coefficient of discharge will be lesser than that of Venturi meter. So this will range in have a value in the range of 0.55 to 0.65. And why is that so? Since you are suddenly constricting the width of the pipe, so there will be a lot of eddies formation in this region, and also a lot of eddies formation in this region. So this will create more amount of losses in the orifice meter, and this will lead to a lower value of the coefficient of discharge. Okay, so these are the two measuring and two instruments that are used to measure flow in pipes. Okay, now we'll go through the laminar flow through pipes. So how the shear force and the pressure gradient are related in fully developed pipe flow. So the net shear. So this derivation we have done before also while we are studying laminar flow. The thing is that the net shear, if you take a cuboidal control volume inside the flow, there will be two shear stresses, one at the bottom surface and one at the top surface. So bottom surface the shear stress will be tau and the top surface will be tau plus del tau by del y into dy. And there will be a pressure difference between the two vertical surfaces. So there will be, if you pressure P on the left surface is P and the pressure at the right surface is P plus del P by del x into dx. So since there are two forces will be balanced when you are taking flow through pipes. So to balance the two forces, we will finally get a relation between the shear stress and the pressure gradient as del tau by del y is equal to del P by del x, and del tau by del y can be obtained from Newton's law of viscosity. If we take a linear if we take a linear profile between the shear stress and the rate of strain, that is tau is equal to mu du by du. If we take this, then the pressure, change in pressure between two sections will be given by this formula, that is mu del square u by del y square into del x. Thus the pressure, change in pressure is linearly related to the distance between the 2 points in case of for fully developed pipe. Okay, so this is one thing. Now if we take a laminar flow through a circular pipe, this is also called the Hagen-Poiseuille flow. So here we take a control volume which is cylindrical in shape like it is shown here. So the shear stress along the surface will be tau and the pressure between the left surface is P and the pressure at the right surface is P plus del P by del x into dx. So if we balance the forces and get the equations, so this is this derivation also we have done before while studying laminar flow. So the velocity of at any point in the cross section is given by this formula. It is 1 by 4 mu minus del P by del x into capital R square minus small r square. So small r is the distance of the section from the center of the pipe and capital R is the radius of the pipe. So this is the velocity at any distance from center. Velocity will be maximum at the center since small r will be 0, so it will be 1 by 4 mu minus del P by del x into r square, capital R square. And if we average this value along the cross radius of the pipe, diameter of the pipe, we will get the average value. And this average value, mean velocity, average value or the mean velocity is given by this formula, 1 by 8 mu into minus del P by del x into r square, and this is equal to half of V max. V max is where the maximum velocity at the center of the pipe. now the third formula is the head losses. When we are taking a circular pipe, the head loss is given by the Darcy-Weisbach formula, that is FLV square by 2GD. And if we substitute F as 64 by RE, that is for laminar flow, we get the head loss due to friction as 32 into mu VL by W into V square. And last but not the least, it is the pressure drop. The pressure drop between two sections in the circular pipe is given by P1 minus P2 by L is equal to 32 into mu V by D square. So these formulas we have to remember, because these are very important formulas when you are solving problems related to pipe flow, that is laminar flow in pipes, especially when it is circular pipes. And then this there is a derivation. The friction losses are given by two formulas. One is the Darcy-Weisbach formula that we mostly use in case of circular pipes or even pipes of any cross section, and you can also use that in open channels also, but it doesn't but the experimental values of friction losses in open channels are doesn't match properly with this Darcy-Weisbach formula. So that's why we go to the Manning's formula or the Chase's formula for open channels. But for pipe flows, Darcy-Weisbach formula is the most widely used formula for friction losses. And this formula, the formula for friction losses can be obtained using the Bernoulli equation between two sections. So the if we consider two sections in a pipe, so let us take a circular pipe. This is section 1 and this is section 2, and there is no width constriction. So if you write the Bernoulli equation, it will be like this: P1 by W plus V1 square by 2G plus Z1 equal to P2 by W plus V2 square by 2G plus Z2. Now V1 will be V2 equal to V2 since there is no width constriction, and also Z1 is Z2 equal to Z2 since we are not taking an inclined plane. The pipe is considered horizontal, so the datum head is not changing with distance. So the pressure loss, that is head loss due to friction, is given by P1 by W minus P2 by W. Now if we let F dash be the frictional resistance per unit area at unit velocity, then the frictional resistance is given by F dash into PL into V to the power N. Where P is the weighted perimeter of the pipe. So if we take a circular pipe, so this is the perimeter of the pipe, and if we take the length L, so it will be total area that is weighted in the pipe, that is P into L and V to the power N. So we will be taking the friction losses to will be proportional to the V to the power N. We can N, we have to find out N. So this will be coming from experimental values only. Now the at section 1, the pressure force will be P1 into A, and at section 2 the pressure force will be P2 into A. Now the difference between the two pressure forces will be P1 will be the frictional resistance, that we got this as the frictional force. So P1A equal to P2A plus frictional resistance. So if we rearrange the term, we can get P1 minus P2 is equal to F dash into P by A into L into V to the power N. Now If we divide both sides by the specific weight, we will get the head loss due to friction as F dash P by F dash into P into L into V to the power N by W into A. Now A by P is called the hydraulic depth. Sorry, it is called the hydraulic radius. So it is represented by the value R, it's also called R. So if we take a pipe that is running full, that is the weighted perimeter is equal to 2 pi into R. In that case, if we substitute the values for A and P, we will get R is equal to D by 4. Now, and we will be assuming n equal to 2, and this comes from experiments, that is experiments we get HF is proportional to V square. So the final formula that we get is HF equal to FL V square by 2G, where F is a friction factor and is related to the frictional resistance as 4F dash. F dash is the frictional resistance. So this is the head loss due to friction in pipes. We can mostly when the pipe is circular. So, and this is okay. So now we'll hope there are no doubts in this. I think we have already gone through these formulas before also. So now there are some other losses that are there in a pipe, that is if there is sudden enlargement of pipe or there is sudden contraction of the pipe, and these are given by these formulas. So if there is sudden enlargement, then the head loss, these are minor losses, the values are not that much, but it might play a significant role if all the factors are accumulating in together. And friction losses are small, that is the length of the pipe we are considering is small. In that case, minor losses will be of comparable magnitude to friction losses. So one thing is head loss due to enlargement. So this will be given by the value V1 minus V2 whole squared by 2G. So if we sudden enlargement, this is V1, this will be V2, V1 will be greater than V2. So the friction loss of energy is given by V1 minus V2 whole square by 2G. When there is sudden contraction, suppose if this pipe is like this and there is a sudden contraction like this, so in that case it will be given by 0.5 V square by 2G, where V is the velocity before contraction. And loss of energy due to entrance of a pipe, suppose if there is a reservoir and we fit a pipe here, and so when the water is moving to the pipe, there will be some head losses in this part, and this will also be equal to 0.5 V square by 2G. So these three are done. Then there is a loss of energy due to exit from a pipe, that is if we are filling a bucket or a pipe, filling a bucket or a reservoir through a pipe, then also there will be some losses when it is entering the reservoir or the bucket. So this is loss of energy due to exit from a pipe. So this is higher than that of loss of energy at entrance, so this is given by V square by 2G. Again, V is the velocity of the flow in the pipe. And there is some loss of energy due to gradual contraction and enlargement. So this was sudden contraction, so there might be gradual contraction also. If there is gradual contraction, then it will be K into V1 minus V2 whole squared by 2G. The values of K depends on the how much what is the slope for the contraction or a slope for the enlargement. There may be some losses in bends also, and this is also given by k into v square by 2g, and this also depends on the angle of the bend. If we take a 90-degree bend, or we take obtuse angle bend like that, so depending on the angle of the bend, the losses will be different, and this value of k will be depending for angle of bend if we take the same material for pipes. And there are some pipe fittings. If we fit a nozzle or a valve in pipe, there will be some losses there also, and this will be given by k into p square by 2g. So these are minor losses. So when taking friction losses for a long distance, we generally neglect these minor losses. Now we'll go to a concept called a siphon. So what is a siphon? Siphon, suppose there are two reservoirs separated by some distance. Now we have to fill one reservoir from the other reservoir, like through a pipe. But thing is that between the two reservoirs there is a hill. So we have to lay the pipe on top of the hill, and then only it can go to the other reservoir. So this is the schematic for a siphon. If we take this as an inlet reservoir, and this as the outlet reservoir. So this is the water level at A. It will be at higher elevation than the water level at B, and this is the hydraulic grade line, that is the surface. And remember that since this is the pressure at the surface is P atm, here also it is P atm, and throughout the length of the hydraulic grade line, the pressure will be P atm. atm is the atmospheric pressure, since it is connecting the two free surfaces of the reservoir. And a total energy line will be slightly higher than that of the hydraulic grade line, and this distance gap is given by v squared by 2g. And when suppose we are fitting so this is a siphon, it is connected to the inlet reservoir, it is rising above due to the hill or the obstacle in between, and then it is going to the outlet reservoir. So there will be some losses here in the entry section, and these losses are given by 0.5 v squared by 2g. Okay, so now the thing is that since the hydraulic grade line, it cuts the siphon at 2 points. So if the part of the siphon that is below the hydraulic grade line will have a pressure that is higher than the atmospheric pressure, but the part of the siphon that is above the hydraulic grade line, the pressure will be less than the atmospheric pressure, and this is the summit, as the top point of the siphon. This will have the minimum pressure. Now the thing is that for flow to take place between the two reservoirs, there should be some difference in head, then only there will be the flow will be taking place. So since the water has to rise in the siphon, the thing is that it can, and in this point the pressure is reducing, so it can go only to a minimum value. So what minimum value should be the we can consider for the pressure at the point S. So this should be greater than equal to P atm. So P atm is approximately something around 10.3 meter, I think, if we take tell in terms of head. then it is approximately around 10.3 meter. So this is theoretically, but so it should be greater than equal to P ATM if this pressure at point S is less than P ATM, that is it is less than, much less than this atmospheric pressure, then the water won't be flowing from A to B. So there will be some vapors or eddies formation in this region, and this will lead to this can also lead to a lot of non-linear losses, and also there will be some high vapor pressure. So there won't be any flow between the two sections, and this is theoretically the minimum pressure at summit is 10.3 meter, but in practice this value comes around 7.8 meter, because since we are already considering some losses in the pipe, that is in the siphon, as we are connecting through a distance between the two reservoirs. Okay, so I hope this is clear. So now considering that the two that the pressure at the summit edge is greater than atmospheric, that is sorry, this is minus 10.3 meter, sorry, not plus. So it can reduce to minimum of minus of atmospheric pressure, not atmospheric pressure, sorry, since this is value is already less than atmospheric pressure, it should not be less than minus of that atmospheric pressure. So this, we are assuming that these conditions are met, that the pressure at summit S is greater than minus 10.3 or minus 7.8, and there is a flow between, and the flow is taking place between the two reservoirs. So there are no losses, there are no eddies or vapors, vapor formation of vapors in the siphon, and in that case we can apply the Bernoulli equation between the two sections there, which is between A and B. So by applying the Bernoulli equation, we can get the head difference between the two reservoirs as 0.5 v square by 2g. This is loss at the entrance of the siphon. Then this is the velocity head, and this is the friction losses. So the head difference between the two reservoirs is v square by 2g into 1.5 plus fl by t. So now if we know the discharge q, we can get the velocity of we can get the value of v, and also the value of f can be obtained based on the flow being laminar or turbulent, or it can be obtained from Moody's diagram also, and then we can get the head difference between the two sections. So this is how we can use a siphon for transmitting water between two reservoirs when they are separated by some distance, and also there is a hill or a hillock obstacle in between. So this is all about siphon. Okay. Now there is let us see what are the head losses that we encounter when we take a tapered pipe. In general, our we will be considering only circular pipes when the diameter is not varying that much, but if the pipe is tapered, then there will be slightly changes in the head losses due to friction. So how do we calculate that? So this is a this formula is, we will derive the formula, and there might be some questions related to this formula in GATE or any competitive examination. So let us take two sections, section 1 and section 2. At section 1 we have the diameter is d1, and section 2 the diameter is d2. So if we now, since this is a trapezoid, this is trapezoidal section, So the ratio of two diameters d1 by d2 will be proportional to the length, and this length is coming from a point O where the two sections meet. So this will form a isosceles triangle. So in that case, the distance from the center, distance from the tip to any point is proportional to the uh, diameter at that section. So d1 by d2 is equal to L plus L by L, where L is the distance of d2 from O, and capital L is the distance between d1 and section 1 and section 2. Now based on this, we can obtain the small l as d2 into capital L by d1 minus d2. Now we know that the value of friction loss will be varying from one section to another. So this will be there will be a continuous variation between the of the friction losses. So in that case, what we have to do, we will have to integrate the friction loss from section 1 to section 2. So let us take an arbitrary section in between of with dx and diameter d. So in that case, first let us find what will be a diameter d. So this also we can obtain based on the law of isosceles triangle. d2 by d is equal to L plus x by L plus x divided by capital L, and so small d will be coming as d2 into L plus x by L. Now for a small length dx, the friction losses, the d of hf, this is small friction losses, will be f L v square by 2g d. What will be L? L will be dx, since we are taking a small cross section. So now again v is equal to q by area is pi d square by 4. So we will substitute v square based from q square. So we will get this formula, and now we can integrate the from diameter from 0 to L, that is from 0 to distance L, and we can get the total head loss. So total head loss is given by this formula in case of a tapered pipe. So the main funda here is that you will have to remember that there will be continuous variation in the head loss. So we will have to always integrate the value between the two sections. So last concept before we'll start solving some problems, is how to the transmission of power through pipes. So how do we transmit power? So the when we are transmitting power through a pipe, so it will be depending on the total discharge and the total head. So if we take h as the total head and the small hf is the loss of head due to friction, then the head and the outlet will be given as h dash equal to h minus hf. So we have one section, suppose the total head is h, we have to transmit to another region. So and there will be friction losses in the pipe. So the head here will be h minus hf. Now we know hf is equal to FLV square by 2 GD. The power and the outlet will be given as, so this is a formula for power, that power is equal to weight of water into head available. Weight into head. So the power at this outlet is equal to weight of water will be specific weight of water into Q. So W into Q into h minus hf. So we'll substitute the values. Q is equal to V into area is pi d square by 4, and hf is FLV square by 2 GD. Now if we want to transmit maximum power uh, between the 2 points, then the rate of change of power with respect to velocity should be equal to 0 for maximum power transmission. So we have to differentiate this power formula, and if we differentiate, we will get that the total head that should be available should be 3 times the head losses due to friction. In that case only we can transmit maximum power. And efficiency of power transmission eta will be given by h minus hf by h. I hope this is clear. If there are any doubts, you can ask me now, and then we will proceed to the questions. Okay, if there are no doubts, we will proceed to the solve some questions. The first question is the coefficient of discharge of a venturimeter ranges from 0.95 to 0.99. We have seen in the very initial derivation that since here there is gradual contraction and gradual expansion of the pipe, the the coefficient of discharge will be in this it will be in the range of 0.95 to 0.99. Second, okay, so for a fully developed pipe flow, how does the pressure vary along the length of the pipe? This also we have seen, it varies linearly. How? There is a relation between shear stress, this here, between shear force and pressure gradient in fully developed pipe flow. We have found that the pressure gradient is balanced by the rate of change of shear stress along the cross section, and this will be the formula for change in pressure, that delta P is directly proportional to delta X. So it varies linearly along the distance. So these kind of questions can come in GATE also, so remember. Which of the following factors decide whether the flow in a circular pipe is laminar or turbulent? So it is the Reynolds number. If the RE is less than 2000, it is laminar, and if RE is greater than 4000, it is turbulent. This also we have seen while we are studying laminar flow and turbulent flow. For laminar flow in pipes, the momentum correction factor is, so what is the momentum correction factor? It is the factor that is a different ratio of momentum of the flow based on actual velocity divided by momentum based on average velocity. So 1 by a v square into integration of u square dA. This is the momentum correction factor. And for a turbulent flow, the momentum correction factor is higher than uh, 1 rear to 1.2, and for laminar it is 1.3. This comes from experimental values only. Next, okay, a liquid flows through two similar pipes 1 and 2. If the ratio of their flow velocity is v1 is to v2 is to 3, what will the ratio of head loss in the two pipes? So let us take hf1 by hf2. So the head loss will be proportional to the Darcy-Weisbach formula. So now it is telling that the two similar pipes. So F and F are same, L1 and L2 will be same, and also D1 and D2 will be same. So this ratio will be equal to V1 square by V2 square, which is equal to 2 square by 3 square equal to 4 by 9. Next question, if the, these are very simple questions, I hope there are no doubts here. If the flow rate of water in a pipeline is doubled, then the pressure drop will be dash of the original value. Okay, so how will you solve this? So if we let us consider laminar flow. Now in laminar flow we have for laminar flow we have seen that the pressure drop is given by this formula, this P1 minus P2 equal to 32 into mu v L by d square. This is for the laminar flow in circular pipe. So yeah, if so we have to find the pressure drop. Now what they are saying that the flow rate is doubled. So Q2 is equal to 2 into Q1. Now make delta P is equal to P1 minus P2, 32 into mu VL by rho G T square. And V we can replace by Q by A, 32 into mu Q L by A d square. Therefore delta P is directly proportional to Q. So now it is, so delta P2 by delta P1 is equal to Q2 by Q1, and Q2 is 2 times Q1, it is given. So delta P2 will be 2 times delta P. So it will be option B. Next question. Now head loss at the exit of a pipe. So it is V square by 2G. We have seen through the minor losses. At the entrance of the pipe, it is always 0.5 V square by 2, and at exit of a pipe, it is V square by 2G. You have to these values are empirical values only, so these derived based on a lot of experiments. Okay, now the water flows through a circular tube. with a velocity of 2 meter per second. The diameter of the pipe is equal to 0.14 meter. Take kinematic viscosity as 10 to the power minus 6 and density is equal to 1000. So what is the Reynolds number? Reynolds number is equal to rho v d by v, which is equal to v d by v. We have 2, d is 0.14, and the nu is 10 to the power minus 6. So if we calculate, I think we will get around 2.8 into 10 to the power 5. The correct option is answer D. These are very simple questions. Okay. Next question. When a problem states the velocity of a water flow in a pipe is 20 meter per second, so which of the following velocities is it talking about? So when we say that the flow velocity is something, then we always mean that it is the average velocity. We never say the maximum velocity. If we mention maximum, then we will have to mention maximum. But in general, if we say that the velocity is something 20 or 10, then we always mean that it is the average velocity. Which of the following is, question number 10, which of the following is correct? So the Darcy-Weisbach formula is generally used for head loss in flow through both pipes and open channels. We don't know. Darcy-Weisbach formula is only used for pipe flows. Chase's formula is generally used for head loss in flow through both pipes and open channels. No, Chase's formula is used for open channels. Darcy-Weisbach formula is generally used for head loss in flow through pipes, and Chase's formula for open channels. Yes, this is option C. Which of the following represent a Darcy's friction factor in terms of Reynolds number for laminar flow? This also we have seen through the derivation, that F is equal to 64 by R. For turbulent flow, it is 0.3165 Re to the power 1 by 4. Okay, the final one more question. In a turbulent flow in a pipe, the friction factor F is 0.02. Estimate the ratio of shear velocity to mean velocity. We have seen before that shear velocity is given by V star. It is equal to under root tau by rho, and so V star by mean velocity is given by under root F by 8. So this derivation was done while we were studying turbulent flow and laminar flow. In that case, so if you get, so the friction factor is 0.02, and so it will come as 0.05. Just go through previous lectures. That is, I think week 3 or week 4. I think we have derived how the shear velocity varies for, and how it is obtained for laminar and turbulent flow. Okay, now we will solve some subjective problems. Okay, so first let us go through the question. The population in a city is 8 lakhs, and it is to be supplied with water from a reservoir 6.4 kilometer away. Now water is to be supplied at the rate of 140 liters per head per day, and the half the supply is to be delivered in 8 hours. The full supply level of the reservoir is 180, and its lowest water level is 105. The delivery end of the main is at RL 22.5, and the head required there is 12 meter. Find the diameter of the pipe. Take F is equal to 0.04. Okay, let us have a schematic. So if we take, this is the reservoir, so a pipe is connected. We am just showing a straight pipe. It can be uh, there can be bends and all small minor losses too. And suppose this is a supply tank. This is a supply tank, and from there it delivers to whole city. This is the reservoir. Okay. So this distance is 6.4 kilometer. Water is to be supplied at 140 liters per head per day. Per day. The full supply level is 180. The lowest level is 105. Okay, there are two supply levels. The highest level is 180, and for the minimum level from which the water can flow is 105. Now the delivery end of the main is at RL 22.5. So we take this as delivery. This is at 105. Sorry, not 105. This is at 22.5, and a head required here is 12 meter. Find the diameter of the pipe. Okay, let us solve. First, population is 8 lakhs. So what is the total daily supply of water that we need? So total population is 8 lakhs into 140 into 10 to the power minus 3. 10 to the minus 3, why? We are converting liters to meter cube. So it will be meter cube. So if we substitute, I think we will get around 11.2 into 10 to the power of 4 meter cube. Okay. Now this is a total daily supply, and this supply has to be given in 8 hours. This has to be supplied in 8 hours. So how do we proceed? So if this has to be supplied in 8 hours, then the thing is that into 10 to the power 4 divided by 8 into 60 into 60, and this will come, I think, around 1.94 meter cube per second. So this total water we have to supply in so this is supply, so this is equal to, this surge equal to 1.94 meter cube per second. uh, sorry, so one more thing is, this is not full supply, it is half of the supply is to be supplied in 8 hours, so there also be divided by 2. So supply in 8 hours, so this total supply divided by 2 into 8 and then if we multiply 16 to 60 we will get the units in meter cube per second. So the discharge, so the thing is that out of 11.2 into 10 to the power 4, this total volume, half of this, half will be in the 8 hours and the other half will be in the remaining 16 hours. So for this 8 hours the discharge that we need is 1.94 meter cube per second. Okay, now there are two conditions. Number A, when reservoir is full. When the reservoir is full, what is the head available? The available head will be how much? Total head is, it was 180 minus of the head required at the outlet is 22.5 minus of 12.5, sorry, minus of 12. Okay, so this 180 and 22.5 and 105 are the RL, that is level from the datum, common datum. So the head available at the outlet is 145.5 meter. Now since we are taking the distance as 6.4 kilometer, 6400 meter or 6.4 kilometer, so we can neglect minor losses. So if we neglect minor losses, so by from Darcy-Weisbach equation, so this value will be FLV square by 2G. So this is a total head that is lost when we have supplied water from full water level to the tank with RL of 22.5. So F, value of F is given as 0.04. So we substitute the values. V, you can substitute Q square by A square. 0.04. L is 6400 into U square 2 into G into the diameter of the pipe we have to find out. Into pi by 4 into d square of whole square. Since it is area square, Q square by A square will be coming, so pi by 4 whole square into d square. So it will bring d to this side, d to the power 5 will come, 0.04 into 6400. Q will be 1.94, 2 into 9.81 into square by 4 square into 145.5. So I think this will come around, if we solve, D will be coming around 0.886 meter. So if we are supplying the water with full head, then the diameter of the pipe required is 0.886 meter. Now if you are supplying water with the lowest head, that is when RL is 0.105. Case 2. Water supplied at lowest RL. In that case, so head available, that is head lost, is 105 minus 22.5 minus 12. This will come around 70.5. So again, using the formula for using Darcy-Weisbach formula, 70.5 equal to FLQ square by 2GT into. So if we substitute the values here, D will come around 1.025. Okay. So the thing is that when you are for the maximum, when we are taking the maximum head, D comes around 0.886, and we are taking minimum head, D comes around 1.025. Now for practical purposes, we will be taking the diameter of the pipe as 1.025 or slightly more than that, since there will be some other minor losses also in the pipe. So to encounter those losses and to take and to make the flow smoothly from the reservoir to the city, we will be adopting this value. Okay, so I hope this is clear. This is just you have to solve a numerical. And any doubts in this question? Okay, if there are no doubts, we will proceed to the next question. Okay, so what is the question given here? The two pipes of 300 meter long are available for connecting to a reservoir from which a flow of 0.085 meter cube per second is required. If the diameter of the two pipes are 0.3 meter and 0.15 meter respectively, determine the ratio of the head loss when the pipes are connected in series to the head loss when they are connected in parallel. Okay. So Q is equal to 0.085 second. Diameter of the first pipe is 0.3 meter. We have to head HF in series. We have to find a ratio when the head loss due to head loss when they are connected in series and head loss when they are in parallel. Okay. So now when they are connected in series, suppose, so this will be some length, this will be some length. So the total head loss will be the sum of this head loss and the discharge will be same for both the pipes. So Q will be here, so it will be Q will be coming here also. So this is for series connection. So head loss will be HF in the series will be FL V1 square by 2 G1. So and L1 is equal to L2 is equal to 300 meter. This is also given, plus FLV2 square by 2 G D2. We can take FL and 2G outside FL by 2G 5 by 4 whole square into d2 d1 to the power 5 plus q2 square by d2 to the power 5. Both q will be same, so yeah, I think it will be f into 300, q will be 0.085, 2 into g into 1 by 0.15 to the power 5. Okay, this is for HF in series. Now HF in parallel. In this case, the two pipes are connected in parallel. In this, the total Q that will be coming here will be diverging into two parts. One will be Q1 and the other will be Q2. So when there is the Q is the the total Q will be divided into the two sections. So capital Q is equal to Q1 plus Q2. Now the ratio of Q1 and Q2 can be obtained by based on ratio of diameter. So Q1 square T square is equal to square by 0.15 square. So the Q1 will be approximately 5.65 Q2. And it's the head loss in both the pipes in parallel will be same, that is F L Q1 square by 2G since the pipes are connected in parallel, the head loss in both the pipes will be same. Now let us find what will be Q1 and Q2 since total Q you know. So 0.085 is equal to 6.65 into Q2. Q2 will be coming in around 0.086 by 6.65. So the HF parallel will be around it will be F into L. L is 300, Q2 is 0.086 whole square, 2 into G into pi square by 4 square into D2 is 0.15 power 5 into 6.65 whole square. So now if we take the ratio, I think HFP you can calculate the value. I think it will come around 45.7. So the head loss in series is always greater than than HF head loss in parallel. So this is an important inference. Okay, I hope this is clear. Okay, let's go to the next question. If there are any doubts, you can ask me. I am not doing the detailed calculations here. You can do it simply using calculator. So I am just showing how to solve the concept behind solving this problem. Okay, if there are no doubts, proceed to next question. Two reservoirs are connected by a pipeline which rises above the level of the highest reservoir. What will be the highest point of the siphon above this level if the length of the pipe leading up to this point is 540 meter, and diameter of the pipe being 0.35 meter. The difference in level of the two reservoirs is 12.6 meter, and the total length of the pipe is 960 meter. So the siphon must run full. The separation of dissolved gases may be assumed to occur at absolute pressure of 2.4 meter of water. What will be the discharge under above conditions in liters per minute? Assume F equal to 0.04 and allow for the losses. Okay, so we'll just have a schematic diagram. I will copy this siphon diagram, I think. So, okay. Okay, so this is a diagram. So what is given in this question? So the thing is that the head difference, so this small h is given as 540 meter. That summit rises above the level of the highest reservoir. So the length of this pipe leading up to the highest point is 540 meter. The total length of the pipe is 960 meter. So the falling limb will be 960 minus of 540 will be 420 meter. We have to find small h, and what is the difference between the two reservoirs? Difference in level of the two reservoirs is, that is capital H is equal to 12.6 meter. The siphon must run full. The separation of dissolved gases may be assumed to occur at an absolute pressure of 2.4 meter of water. So let us apply the Bernoulli equation, and we have to allow for minor losses, that is entry loss we have to consider. So total head that we have is 12. H is equal to 0.5 v square by 2g plus v square by 2g and plus FL v square by 2g d. F is equal to 0.04. So total head that we have is 12.6, and if we this terms as 1.5 plus FL by D. This we obtain based on derivation of the siphon. So we have to obtain V. So V square by 2G, 1.5 plus F is 0.04 L is total length is 960 and diameter of the pipe is 0.35 meter. D is equal to 0.35 meter. So based on that we get V is equal to 1.49 meter per second. So this is the velocity that we obtain in the pipe. Now we apply Bernoulli between, this is the Bernoulli equation between A and P. Now we apply Bernoulli between A and the summit S. And we can take the datum. What do we take? We take the datum as the water surface, as the at A as the datum. So yeah, let's see how do we proceed. So PA by W. So the total, so the pressure at S is less than pressure at A. So we'll, so that, and at A there is no velocity, and we have taken datum at A only. So the only term that is available here is the pressure at A, and pressure at A, pressure term, pressure head, and pressure at A is the atmospheric pressure, and atmospheric pressure is given by PA. Now, okay, so the datum head from S to A is H. So datum head is H plus 2.4 we have to consider, because this is the absolute pressure. It is given that the gases may be assumed at an absolute pressure of 2.4. So the difference in absolute pressure, difference between the two, the summit and the summit S and the A is 2.4 meter. And then we have to consider minor losses. Minor losses equal to 0.5 V squared by 2G plus the velocity head V squared by 2G plus F L1 V squared by 2G D, where L1 is 540. This is the friction losses. Now PA by W is the atmospheric pressure head, and this is approximately equal to 10.3 meter. How does it come? It comes from PA is equal to 1.013 bar, equal also 10 to the power 5 Newton per 10 to the power 5 Pascal. If we convert Pascal to water head, that is divided by rho into G, we will get 10.3. So we have to calculate head. Then the absolute pressure is 2.4 plus, I think it is, if we take V square 1.449 whole square by 2 into 9.81, so it is 0.5 plus 1.5 plus 0.04 into 540 divided by diameter is 0.35. If we substitute, we will get small h equal to 0.75 meter. Okay, so the summit can rise to a maximum of 0.75 meter from the surface of A. That is the highest water level at A. And finally, what we have to calculate? We have to calculate what will be the discharge under the above conditions in liters per minute. So third part is U is equal to A into V, pi d square by 4 into V. If you substitute, it will be coming around meter cube per second. If we convert to liters per minute, to 10 to the power 3 liter divided by 60, it will be around at 8.6 into 10 to the power 3 liter per minute. I hope this is clear, right? Any doubts in this question? If there are any doubts, you can ask me now. Okay. If there are no questions, we will proceed to the next question. This is about transmission of power. So power is to be transmitted hydraulically to an accumulator at a distance of 8 km by means of a number of 100 mm pipes laid horizontally, for which the coefficient of friction may be taken as 0.03. F is equal to 0.03, L is equal to 8000 meter, and D is equal to 0.1 meter. So we can use the the pressure at the accumulator is maintained constant at 6.652 kilonewton per meter square. So this is approximately around 665.04 meter. Determine the minimum number of pipes required to ensure an efficiency of at least 92% when the power delivered is 162 kilowatt. Efficiency is 0.92. So if efficiency is 0.92, so this is given by the formula H minus HF by H. Now H minus HF head at that is at accumulator. We have this head. So this is the outlet head. Since if we take capital head as the capital H as the inlet head, HF is the friction loss, and the inlet head minus the friction loss will give the outlet head, and this is equal to 665.04 divided by H equal to 0.92. From this we get H is equal to 722.87 meters. Okay. Now based on this formula we will get friction loss equal to capital H minus of 665.04. So this will be approximately around 57.83 meter. So we will use the Darcy-Weisbach formula here. F L V square by 2GD so let us substitute. F is equal to 0.03, L is given as 8000 into V you have to find out. 2 into 9.81, diameter is 0.1 is equal to 57.8. From this we obtain V as 0.68 meter per second. Okay, so the power transmitted, what we have to find, determine the minimum number of pipes required to ensure when the power delivered is 162 kilowatt. The power transmitted in kilowatt is how it is given, WQ into H minus HR divided by 1000 because we have to find in kilowatt. W into Q is what, weight of the water, and H minus HR is the head. Okay, so we have to determine the minimum number of pipes. So minimum number of pipes required. So the thing is that when you are using and suppose let number of pipes is equal to n, and yeah, so the most important thing is that when you are want to get high efficiency, we will be using pipes in parallel connection. Why? Because the head loss in parallel connection is less. Okay, so if we take n number of pipes, so the total discharge will be is equal to what, A into V into n. A is 5 by 4 into D square into V into n, 5 by 4, and D square will be how much? I think D is given as 0.1. Yeah, D is 0.1. Velocity we found out 0.68 into n. So Q will be equals to 5.4 into 10 to the power minus 3 into n per second. Okay, so now we have the formula for power. We will substitute in power formula. So we have power as 162 kilowatt. Now W is rho G Q, H minus HF we have around, H minus HF we have 665. So rho is 1000 into 9.81. Q is 5.4 into 10 to the power minus 3 into n into 665.04. So if we solve this, we will get n is equal to 4.6. So 4.6 means approximately equal to 5. pipes in parallel for 92% efficiency. Okay, now second part, also determine the maximum power that can be transmitted. So to do the maximum power, we have to use this formula. What we obtain that? The condition for maximum power transmission. So the head should be equal to 3 times the head loss due to friction. So H equal to 3HF. So for maximum power transmission, the head loss due to friction should be 1/3 of the total head, that is total initial head. So initial head we have, I think we got 722.87 divided by 3, it will be around approximately equal to 240.96 meter. So we have itself. Now we'll use the Darcy-Weisbach formula. FL v square by 2GD is equal to 240. F is equal to 0.03. L we have 8000. V square we have to determine into 0.1. So if we substitute, I think we will get V is equal to 1.404 meter per second. Okay. Now we have already got the number of pipes is 5. So the total discharge by 5 pipes. Q is equal to 5 into Q each, into 5 into 5 by 4 into G square into V. This will come, I think, around 5.513 into meter cube per second. So we have obtained Q. Now after getting Q, we have to find the maximum power. So the maximum power is equal to WQ H minus HF by 1000. So 9810 into H minus HF is 722.8 minus 240.9, and I think this will come around 260.6 kilowatt. Okay. I hope any doubts in this question you can ask me now. I will take I will wait for a minute, and then we will see the last question for the day. You can tell in text if there is any doubts. Okay, if there is no doubts, then we'll see the last question. So this is a question from example. So for laminar flow of oil having dynamic viscosity 1.76 in a 0.3 meter diameter pipe, the velocity distribution is parabolic with a maximum point velocity of 3 meter per second at the center of the pipe. Calculate the shearing stress at the pipe and within the fluid 50 mm from the pipe wall. So if we take this as the pipe, so this is the velocity distribution. So here max will be at the center. So average velocity is equal to half of V max. This will be around 0.5 meter per second. Now del P by del S is P1 minus P2 by L32 mu V by T square. This is for laminar flow. You can get del P by del X as 940. Substitute the values, you will get 941.87, and from that we can get the shear stress tau naught is equal to minus of del P by del X into R by 2. The shear stress at the wall shear stress, it is del P by del X. We substitute R is equal to 0.3 and we will get 70.64. Now the shear stress at 50 mm from the pipe wall. So and from the pipe wall it will be minus del P by del X into R by 2. R minus R by 2. So it is 0.15 minus 0.05 by 2, so it will be 47.09 Pascal. Okay, simple equation of laminar flow. Okay, that was all for today's session. If there are any doubts, you can ask me. I will be there for 2 minutes. So I will wait for 2 minutes. If there are no doubts, you can leave the session. Yeah, this is the last question. So this is the formula for average velocity, that is half of V max. V max is 3 meter per second. So the average velocity we get as 1.5 meter per second. Now the pressure gradient is equal to 32 into mu V by D square. D we have 0.3, mu also we have 1.76, and V is the average velocity, so we got it from here. So we substitute in this equation and we get del P by del X. This is 941.87. Now if we get the wall shear stress tau naught minus del P by del X into R by 2. R is the radius for a circular pipe. So if you substitute, we will get tau naught is equal to 70.64. Now we need to find tau at 50 mm from the pipe wall. That is, this is 50 mm. At this section, that is, we have to find tau. So the formula is minus of del P by del X into capital R minus small r by 2. So if we substitute, capital R is equal to 0.15, small r is equal to 0.05, substitute, and you will get tau is equal to 47.09. Okay, so you can go through your video will be, recording will be available, you can go through if there are any other doubts. Else if there are no doubts, we can close the session today. Okay, welcome then. You can leave the meeting. There are no doubts.